in this example, we really examine what the population standard deviation has to do with the confidence interval. So we're given some basic information, no application here, just the size of the first sample is 20, the mean of the first sample is 10, the second sample has a size of 26, and the second mean is 13. We're constructing confidence intervals on the difference between the two means, and we're trying to infer what's happening in the difference between the population means. So the first thing we'll notice is that if the population standard deviations are known, then we know that the distribution is a z distribution, a normal z distribution. That can aid us, once we make that decision, in finding the confidence interval for the difference in population means given the population standard deviations for the first and second populations. So remember here there's three steps to any confidence interval. First we need the point estimate, and the point estimate is the best guess we have for the difference in means, so that's the difference in sample means. The sample mean 1 was 10, sample mean 2 is 13, so the difference that we have in sample means is -3. That's our starting point for the confidence interval. Second, we have to cook up the error, and the size of the error, or the width of the confidence interval, is determined by the critical value of z, and then the standard deviations with respect to the sample size of both of these populations. So standard deviation 1 squared divided by sample size 1 plus standard deviation 2 squared divided by sample size. So if we were to plug in this information, we need to find the critical value of z. For a 90% confidence interval, we have a critical value of z from the z table. Here, critical values of z, 90% is 1.645. We'll substitute that into the formula, 1.645 times the square root of the population standard deviation of sample 1 squared divided by the sample size of sample 1, which is 20, plus the population standard deviation of the second sample squared divided by the sample size of the second sample, 26. We'll cook up that number. I like to do this all at one time in the calculator, so 1.645 times the square root of 3 squared divided by 20 plus 4 squared divided by 26. That's 1.697927, yada yada. You see that that goes on for quite some time. So the third step in making the confidence interval is to take the point estimate, the difference between the two sample means, and add or subtract the margin of error to create a lower bound and an upper bound. The lower bound gets the minus, the upper bound comes from the plus of these combinations. So remember the point estimate was -3, and the margin of error 1.697927, 1.697927. So in the calculator it's quite easy to say -3 minus this answer, and then we can pull that thing back up either by going up and pressing enter, or you can do the second and the enter button will pull up the entry. So second enter pulls up the previous entry, and we can change that minus to plus. That gives a lower bound of -4.697927 and an upper bound of -1.302072. So here I'll round to 4 decimal places, 1, 2, 3, 4. This 9 looks next door, the 2 is small, so that part just drops off. And 1, 2, 3, 4, 0 looks next door to 7 and becomes a 1. So the answers are negative 4.6979 for the lower bound and negative 1.3021 for the upper bound. Now that of course is by hand, and we can do this in the calculator as well. If we go to the stat menu, so stat, scroll over to tests and down to what we're trying to calculate. Sometimes it's nice just to look at the list and remind yourself what you're doing. So we used a z-value, we're making a z-interval, but we also had information from 2 samples, so we have a 2-sample z-interval. 2-samp z-int. Pressing enter there allows us to put in the summary statistics or data. If you have raw data, you can put that in the list. We'll put in the stats. The standard deviation of the first population is 3, second is 4. The mean of the first population was 10, or excuse me, first sample was 10, 20 was that sample size. Sample mean number 2 was 13, and sample size number 2 was 26. Confidence level was 90.9. And we want to calculate. So we get negative 4.698 and negative 1.302, which you see is consistent with the confidence interval that we've created, but we needed 4 decimal places, so we did have to go by hand here to get that last decimal place. Now, if both of the population standard deviations are unknown, we cannot use the z-distribution. That means that we need to use the t-distribution. So we have sample standard deviations, but now it's the student's t-distribution, because we don't have the population standard deviations. The degrees of freedom by the traditional method, and that traditional is what we do when we calculate it by hand, is to find the smaller of n1 minus 1 and n2 minus 1. So the smaller degrees of freedom from the 2 samples. N1 minus 1 was 20 minus 1, which is 19, and N2 minus 1 is 26 minus 1, which is 25. So we picked the smaller, which means our degrees of freedom is 19. Given that degrees of freedom and the sample standard deviations, I just want to write down what we had again since it scrolled off my screen. Sample size 1 was 20, sample mean 1 was 10, sample size 2 is 26, sample mean 2 is 13, standard deviation 1 is 3, and standard deviation 2 is 4. The confidence level is 90 and the degrees of freedom is 19. So we can use this together to create the critical value of t. We need the t table. I prefer to look at these on paper. I just have them online so that you can see them from the screen, but hopefully you've printed out your version. Confidence level is 0.90 and degrees of freedom are 19. So we'll scroll down here until those two column in the row intersect at 1.729. So 1.729, because degrees of freedom were 19, confidence level is 90. So the 3 steps for the confidence interval are the same as we saw before. The only thing that changes is the margin of error. First, the point estimate, x1 bar minus x2 bar, best guess for the difference between the 2 population means is -3. Now though, the error is the critical value of t, which we found from the t-table, times the square root of the sample standard deviation squared divided by their respective sample sizes. So plug in the values we have, 1.729 for t, the square root of 3 squared plus 4 squared 3 for the sample standard deviation of the first population and of the second, and then the first sample size was 20 and the second sample size was 26. So let's see what this value gives us. We have 1.729 times the square root 3 squared divided by 20 plus 4 squared divided by 26. An error of 1.78463006 if I write all the decimal places. So step 3 is to take this point estimate and add and subtract the margin of error to find a lower bound where we subtract and an upper bound where it's added. So the point estimate was -3, remember, the difference between the sample means, and then this margin of error, 1.78463006. I'm going to erase some of that actually just so I can fit the calculator and these answers right next to it. But in the calculator I'll keep all of the digits. So -3 minus this answer, and then that same thing but with a plus. So the lower bound was -4.78463, and the upper bound -1.215369. MindTap is asking for 4 decimal places, so 1, 2, 3, 4, 6 stays 6, and 1, 2, 3, 4, 3 turns into 4. That means that this interval is -4.7846 to -1.2154. That's using the traditional method for degrees of freedom. Part E asks us to use Satterthwaite's approximation. Now, this approximation doesn't show up in a great place on MindTap. So if you have this homework open, on the right hand side has the formulas, so you see how to estimate these things. The Satterthwaite approximation is mentioned here, but the formula is down here. So I think that's part of the problem, is that he's out of place. And I've told the developers and asked that they put him back up here where he's mentioned. But this is the formula for the degrees of freedom when we use this approximation. So I'm just going to snip it rather than rewrite it. Here. So we have all these values, they're listed up there, to calculate a new degrees of freedom. Traditionally, remember in part C, we found the degrees of freedom was 19, but now we're going to use a more accurate and larger degrees of freedom from this approximation thanks to Satterthwaite. To do that, I'll just punch it directly in this calculator, all of it at the same time. So I'm following this formula with those numbers. The numerator is S1, 3, squared divided by the sample size 20, plus S2, which is 4 squared divided by the sample size of the second sample 26, and all of that is squared. And we want to divide by a whole bunch of stuff down here, so open a parenthesis, and 1 divided by 1 less than the first sample size, so 19, times the standard deviation of the first sample, 3 squared divided by the sample size 20, and that whole term itself is squared, plus 1 divided by 1 less than the second sample size is 25, times the standard deviation squared divided by the whole sample size 26, and that whole term squared, and that completes the denominator. So that's quite an ugly thing. If you punch it in with me directly, you'll notice that I had extra set of parentheses here and here. I did these numbers in my head, so I didn't make subtraction. I just called that one 19 and I called this one 25. And then the rest looks just like it does there. That gives us a degree of freedom of 43.984. Which is exact, but not listed on the table. The table that we are provided with goes for degrees of freedom of 40 or 45. Those are your options. And let me remind you what that looks like. Degrees of freedom on the left, once you get to 40, it just skips right to 45. And the reason that is because when you're down here with higher degrees of freedom, the difference between these t-values aren't very much. That being said, there is some difference, and if these things were going to 4 decimal places instead of 3, you'd see the difference a lot more. So traditionally what we would do is use the most conservative value of t, which is 40, and our confidence level was 90, remember, 0.9, so we'll scroll down here. And they coincide at 1.684. That gives a critical value of t of 1.684. The thing is that we use 40, and the reason we use 40 is more conservative, so we wouldn't want to go high. That keeps our confidence interval a little bit wider just to make sure we hit that confidence level. And we can calculate all the same stuff as before. Margin of error is, or point estimate is -3 from step 1. Number 2, the margin of error is the critical value of t times the square root of s1 squared over n1 plus s2 squared over n2. But now the critical value of t is the new thing. That's from the approximation of Satterthwaite. This guy is 1.684. Times the square root of 3 squared over 20 plus 4 squared over 26. Now, I did this in my calculator before I started the video, and I got 1.73818,219. If we use those to create the lower and upper bound in the same fashion, the lower bound I got was -4.73818, and the upper bound of -1.261817. To 4 decimal places, 1, 2, 3, 4. The 1 will turn into a 2, and 1, 2, 3, 4. The 8 stays the same. So we see a lower bound of -4.7382 and an upper bound of -1.2618. The thing is, if you enter this into MindTap, they are marked wrong. And that's because of this approximation we made here. The best we could do was 40 degrees of freedom, but really we should be able to get at least 43. This is not a wrong process, and that's why I think that there's some frustration about how to get this answer correct, or why it keeps being marked wrong. So we have 2 options. The first option is to look online for an extended t-table. I found one here, easycalculation.com, and the degrees of freedom are listed. So here we could find exactly 43 degrees of freedom and go over here to find the appropriate t value. Or we can use a calculator, and the calculator I think is a little more direct and a little bit easier way to do it. Satterthwaite's approximation is used by all technology to find these confidence intervals, so we don't have to do anything too special in here. We just have to find the confidence interval we want to construct, which is a 2-sample t interval. And we have 2 samples, and we're trying to use the t distribution. So on the calculator, we would hit the stat button, scroll over to tests, down to the 2-samp t interval. we'll put in summary statistics here. The sample mean number 1 is 10, sample size, or sample standard deviation is 3 for the first sample, and the sample size is 20. The mean for the second sample is 13, standard deviation is 4, sample size is 26, and the confidence level is 90%. We are not pooling the variances here. We don't have any reason to believe that the variances are the same, so we say no. In fact, we'll say no for this whole section, so don't worry about that too much. Press calculate. See that your degrees of freedom match what we found by hand over here, 43.984. That means that they are using the Satterthwaite approximation. Also, their lower and upper bounds are a little bit different than ours. The lower bound there, negative 4.734, and an upper bound of negative 1.266. You'll see how that's different in the third decimal place than what we found by using this larger critical value of t. So I suggest you do it like this. Mine top marked both of my answers correct, even though I only went to 3 decimal places from the calculator. When I put it in, I think that they must be close enough within the tolerance, but the first 2 are not. Sorry for the frustration. So once this homework is due, I can return to these questions and I'll administer manual credit for answers like this, which are calculated correctly using the table values. You'll have to do that by hand after the assignment is due, or you can use the calculator here, or you can look up the extended t-table and use the values from here to find an answer that will be accepted. I apologize for the frustration. I've asked the developers to look at the level of tolerance in here and accept either value, either one created from the table from their text or one from technology. Of course, if you have any further questions, you're welcome to contact me, and I will be happy to answer the best of my ability.